Okay, now let's consider a more complicated example. Let's say again we have a beam that is fixed to the wall, and then we have different kind of loading. 2K here, 1K, and another 2K here, and another 3K right here. So let's make this, instead of because we already have a 2K, let's put this 3K and make this 4K. Okay, so we have obviously a lot of loading on this beam. It's fixed to the wall. Put some distances here, 1, 1, 1, 1. And now we want to write the moment diagram with just one equation. If we do the traditional method, we have to consider 1 interval, 2 interval, 3 interval, 4 interval. And each one of these intervals give us 2 constant of integration. So 4 times 2 is 8 constant of integration, plus 2 for the wall boundary is 10 constant of integration. So you have to solve 10 equation, 10 unknown. That's a lot of work. Now we want to solve this using Heaviside function. So in order to use Heaviside function, like I said before, you take a reference. Let's take a red color. You take a reference either from left or right. I take it from left, and then you cut it just before the very end part of the beam. So that's my X. And then you make a free body diagram, and then use Heaviside function to express your moment in just one relation. Okay? So before I do that, I want to find the reaction in the wall. So let's say this is the point at the wall is A, B, C, D, E. So I want to find the reactions in the wall. So here, the wall reaction, I have AY, MA, M. Fortunately, this is not very user-friendly. M at A and AY. Then I have 2K right here, 1K, 3K, 4K, and all the distance is given. So I write summation of force in Y 0, that give me AY minus 2K plus 1K minus 3K minus 4K is equal to 0, and summation of moment about point A, the wall is 0. That's going to give me MA positive negative 2K times 1 plus 1K times 2 negative 3K times 3 plus 4K times 4 is equal to 0. So I solve the first equation. AY is equal to negative 2 plus 1 negative 1 minus let's double check this relation. AY negative 2 plus Y 1 negative 3 negative 4, that's right. MA negative 2 plus 1K times 2 negative 3 times 3 negative 4, yeah, negative 3 times 3, and that should be negative. I was suspecting something is wrong, and it is. This should be negative. So MA negative 2K times 1 plus 1K times 2 negative 3K times 3 negative 4K times 4 is equal to 0. So if I solve this relation, the first relation, I get AY is equal to negative 2, negative 3, negative 5. Let's see this relation, put it right here. Negative 2, negative 5, 5K plus 1K, negative 4K. So this is going to be negative 4K, negative 4K, negative 8K. Take it to right, positive 8K. And if you solve for moment relation, MA, this is going to be a positive 2, cancel out with this, and this is going to be negative 9, negative 16, which gives you 5, 25, negative 25, take it to the right, positive, MA is equal to 25 kilonewton, and this kilonewton, positive. So if I want to simply write the numbers here, again, I have this beam, there is a war reaction, AY, which is simply 8K, and MA. Now simply let's just factor out this K so we know we're talking about 1,000, right? So this is going to be 8, and MA is equal to simply 25 to 1, 3, 4, and distances all equal 1, equispaced 1, 1. So that's my beam, and I want to find this moment relation, because moment relation is one I plug in the deflection equation and I double integrate and find the deflection curve, right? And I can solve a lot of problems. So I want to find this moment relation with just one equation, one line. So again, I take my reference from left, let's use green here, and then I cut it just before the very end part of the beam. So that's your X. And if you cut that, you're gonna get a moment like that, MFX, and a shear V of X. I could add an axial load, but here I don't have any axial loading on the beam, so I just ignore it. Okay, so I simply say I write equation summation of moment about point X must be 0. So I get M of X, and then the next thing, don't forget, we do nothing with the right part. You see this part? This is not in our system. This part is not, let's write not in our system. Our system is whatever on the left part of this cut section. So we do nothing with the 4. So I include MX because it's right here on my beam, and I don't include VX because VX is passing through the X. And then the next thing I need to include is 3 right here. So 3 times moment arm. What is the moment arm? X minus 1, 2, 3 inside Heaviside. Then you go to the next one. The next one is negative 1 times Heaviside, X minus 2, and the next one, put it here, is 2 plus 2 times Heaviside, X minus 1, and then the next one is negative the war reaction 8 times X right here. So because it's always there, I don't use Heaviside, right? It's always there. I don't need a switch to make it on or off. So negative 8 times X, finally plus 25. The wall couple moment is equal to 0. That's one line equation for my entire moment. Isn't that beautiful? I don't need to waste 4 or 5 pages of derivation for that, to take 4 different intervals. So let's solve it for mx. So your mx is equal to, and don't forget, because we already factor out 1 kilo, so this mx is in kilo Newton meter, is equal to, take 3 to the right, so you get negative 3 x minus 3 plus x minus 2, negative 2 x minus 1 plus 8x negative 25. That's your final relation for couple moment. Now if I say, well, find the deflection at point, let's say at the middle of the beam, find the deflection at x is equal to 2. What is v, the deflection at x is equal to 2? That's the question, right? I say, well, I have to solve this equation. Second derivative of v is equal to times ei is equal to m of x. Okay, and for this moment, let's say your e times I is equal to 1. Okay, and so therefore, let's say ei is equal to 1,000. So this 1,000 cancel out with the 1,000 that we already factor out of this moment, right? So in fact, you get the second derivative of v with respect to x is just this moment equation that I have right here in kilonewton meter. Okay, so all I need to do, plug this relation right here and double integrate. So that is equal to negative 3x minus 3 negative plus x minus 2 negative 2 x minus 1 plus 8x negative 25. The first integration give me dv dx is equal to negative 3 x minus 3 square over 2 plus x minus 2 square over 2 negative 2 x minus 1 square over 2 plus 8x2 over 2 minus 25x plus c1, the first constant of integration. What is the first constant of integration? If you apply the boundary condition at the wall, you get c1 is equal to 0. Why? Because v of x0 is 0. Now let's go ahead and take the second integral. V of x, the second integral is equal to negative 3 over 2, you already have this, x minus 3 to the 3 over 3 plus x minus 2, 3 over 6, negative x minus 1 to 3 over 3 plus 4x3 over 3 negative 25x2 over 2 plus the second constant of integration, which is also 0. If you apply v at x is equal to 0 is equal to 0. Then your equation of neutral axis, v at any x is equal to negative 1 over 2 x minus 3 plus 1 6 x minus 2 cube minus 1/3 x minus 1 cube plus 4 over 3 x cube minus 25 over 2 x squared. That's what you get for deflection. It's a very complicated relation. If you plot it using a computer program, you see a beautiful cubic curve that shows the deflection of the neutral axis like this. If I can draw it here, hopefully with a, let's use a color we haven't used there. So this curve is going to deflect like that. It's more complicated than just polynomial, like quadratic. You see, we have equation before we solved it was like either like this or going up. This curve is going to have some up or down, some external, like this. Sometimes go up, sometimes goes down like that. It has some min max. So let's evaluate this at point x is equal to, what is the point that I was trying to get? X is equal to 2, highlighted right here. X is equal to 2. So if I put x equal to 2, what is the value of this? At x is equal to 2, this is smaller than 3, so this value is completely 0. What about this? This is also 0. What about this? This becomes parentheses x minus 1, because x2 is greater than 1, right? So if you put 2 here, 2 minus 1, it becomes 1. So your deflection there is negative 1/3 plus, what about this guy right here? Put 2 right here. So you get 4/3, 2 to the 3rd power, which is 8, negative, put again 2 there, 25/2, and if you put 2 there, it becomes 5. 4 times 4. So that's your deflection for at point x is equal to v of x is equal to 2. Look at this. It's less than a page. Do you see that? Now, I recommend solve this problem as a homework. You see, we didn't have so much homework at the midterm, after midterm, because of so much trouble we had with a lot of things. But again, optional homework, you don't have to turn it in. Just solve this problem right here using traditional interval based. That means take one interval from here to here, solve the problem, take one interval from here to here, one interval from here to here, one interval from here to here. Then solve 4 differential equation. Then you get 8 constant of integration plus 2 at the wall, 10 constant of integration. And then solve all the constant of integration, 10 equations, and then evaluate the result in the middle of the beam right here. This point right here. You should get the same result I got right here with just a couple of lines. I hope this helped you to understand this extremely useful Heaviside function, which is used in industry everywhere. And now we want to, in the next example, I want to make this support a little bit more complicated. Right here we have a wall. What if we had, like roller pin? Actually, before I solve that, I want to solve a problem with the distributed load, okay? And show you how Heaviside function works with the distributed load. And then we go to more complicated support reaction like that. Okay.